Okay, so I'm going to continue with conversion instruction support, this time focusing on packed conversions. But before I do that, I just want to fix some forms that I've got here, specifically the VEX or the EVEX conversions with truncation. For these, I allowed embedded rounding, but really I should just be only doing suppress all exceptions. I couldn't actually test these because NASM was incorrectly rejecting this decorator, but it should be suppress all exceptions for these ones. So now I'll just focus on these packed versions, which I can also just, like the Scalar ones, test all sort of in bulk. There are some similar forms between different groups of them, so I can copy-paste tests and things like that. One of the downsides of doing this stuff is that NASM doesn't seem to be very good with its support for knowing where things like embedded rounding and suppress all exceptions are actually valid, so we'll just do what we can and hopefully get some good tests together. So we'll go SSE ASM, and we'll start with a conversion from PS to DQ. So PS and DQ are the same size as each other, they're both 32 bits. So in these cases, the register names are the same, and it makes the test pretty easy to write. So these are all 2 operand, and the operand encoding is always RM. So we'll have XMM0 with XMM1, and then we've got the memory access with RCX. So that's the only legacy one, and then the VEX ones are the same. But the VEX ones here also support YMM. And then we move on to EVEX, which also has op mask and zeroing mask, memory broadcast, and embedded rounding in the ZMM case. So if we just copy this one and do XMM, but we'll do the op masks on the first one. Then we've got broadcast. So this one is 1 to 4, since we're going from a 32-bit element into a 128-bit vector. Then we've got YMM, where the lanes are going to double for the memory broadcast, and then we've got ZMM, where they're going to double again. So that's those ones, I think. Oh, and this one also should have embedded rounding. So we'll do rounding with suppress all exceptions. Then we'll just try and generate these listings to make sure that everything is okay. SSE LST, that's all okay. So then we're going to do PS to well, so this one has a truncated version, basically, so we could do CVT and add another T on here, but I think that this one will not support rounding, but it should support just suppress all exceptions. Yep, that seems okay. Then we just need the same thing again, but we're going to do DQ to PS. So here we'll just change this to DQ to PS and just see if that works. That seems okay. So now we just need the same sort of thing, but instead of PS, it's going to be PD. So we'll change all of these PS instances here to PD instead. And now this is where we're actually going to need to change some things like the register names. So for example, if we're going from the same register to the same register, like vector width, this can only hold 2 64-bit floats in it, and then convert into 2 32-bit floats. If we want to do all 4, then the destination or the PD side needs to be twice the width as the other side, so that we can fit 4 in here and then go to 4 in here, for example. And then with ZMM, if we wanted to go to 8 in here, then we need to use YMM to go to 8. Okay, so convert, yeah. Yeah, okay, that all seems okay. So Basically, we're doing PD is the source for these ones. So let's just find the first PD one, which is here, going to PS. So these ones are okay. For this one, we need to convert to basically XMM. And in these two cases, to disambiguate them, we'll just annotate the memory size. So this one will be O word for 128 bits, and this one will be Y word for 256 bits. Then we've got the same thing going on down here, and this changes to YMM in this case. So for this case, we've got Z word memory and Q word, because Q word being the element size of being 64 bits. So we'll just do these ones as well. This one will be Y word, and then this one will be O word here. Then we've got PD to DQ. Let's just check the rounding as well. The rounding seems like it should all be okay. And because these are PD now instead of to 4, we're actually going to do, this one is, I've annotated the wrong ones here. Let's just undo that. Okay, this one is the one that should be done. So these ones change to XMM. This one is Y word. This one is O word. This one changes to XMM, and then these ones change to YMM. This one is Z word, and this one is Q word. So we've got Q word again, and this one is Y word. And then we've got Q word and O word. So PD to DQ is more of the same, really. So we've got PD to DQ. This is basically the same thing. So we'll just take this one, because this is the truncated version. So we'll just add a T on there. And again, this is not going to support rounding, but it's going to support suppress all exceptions. So if we go to PD to DQ, this has suppress all exceptions support here. And then DQ to PD, we've basically just got it the other way round. So in this case, we don't have to disambiguate between memory accesses, because this already contains all of the information in the destination register size. So for this one, we've basically got YMM with XMM. So this one changes to XMM. This one also changes to XMM, and this one changes to Y. Then instead of 1 to 4, I think we've got 1 to 2, because these are now double the size. 1 to 4, and then 1 to 8. This one also should be 1 to 4. Okay. And then we've just got 2 more to go, which is PS to PD and PD to PS. So these two are similar to each other as well. I think if we do, yeah, we'll do this one first, because it's got a similar structure to this. So we'll do PS to PD. So we've got XMM, XMM, then YMM with XMM. There's memory accesses, but the difference here is that this one is just suppress all exceptions. And then we've got the other way around. So the other way around is basically going to be this annotated version. We'll use this one. So instead of PD to DQ, this is going to be PD to PS. And I think that should all be the same. So if we've got PS to PD, PD and PD to PS. So we've got X, 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 Y. XY, that's okay. And then we've got embedded rounding here. So that should be okay as well. Okay, so let me just check that I don't have any duplicate blocks anywhere. That all seems okay. Okay. This one is also okay. That one's okay. That one's okay. Okay, and so we've got 1, 2, 3, 4, 5, 6, 7, 8. So it looks like I've got all of the instructions here. And the listing seems to be generating correctly. Let's just go and check. So down here I see basically blocks of EVEX, VEX, and legacy encodings. It looks like none of them are really out of place here, so I think it's okay to go and generate the actual encoder tests. So let's just take all of these packed versions here and go to the encoder test. We'll put them down at the bottom here, and we'll just find all of these mnemonics. We'll take these actually and deduplicate them, uppercase them, and add op onto the beginning. Then I can just take these over to the this block over here, and I can also add some empty form tables for them as well. Okay, so let's just get these tests done then. So we'll get all of the convert ones again. Okay, so these need to basically be uppercased and prefixed with op. Then we've got some width, followed by V0 and V1, and then they're all 2 operand encodings, so we'll just put NA, NA. Then we've got these ones with square brackets. So let's just find square brackets with the RX. All of these ones need to change V1 into CX as a memory access. And then all of the cases where we've got 1 to something, we need to find that memory access and change it into a broadcast. Then these cases where we've got SAE, we need to change V1 into SAE. And then in the case where we've got RN SAE, we'll change all of these V1s into embedded rounding with RN for round to nearest. So that takes care of all of the operands, I think. So now we just need the sizes. These two, for example, will be X word. Then we've got X word again, followed by Y word. Then we've got 3 X word for this one, 3 Y word for this one, and then 4 Z word for this one. And then I think it's basically going to follow the same sizes down here. So we'll just replace all of these and all of these ones. Just do this for all of them. Two more to go. This one, is this one a bit different? No, that one seems okay as well. I'm sure that one of these didn't support embedded rounding or anything though. 2PD. So the one that is 2PD from from DQ, this one should not be supporting any embedded rounding. So actually this test here would be incorrect. So let's just get rid of that one. Again, NASM here, just not being very good at deciding on when SAE versus embedded rounding and stuff is actually correct. So DQ to PD, we've got DQ to PD. There is no embedded rounding support on this EVEX one here. So we'll just take this one out and regenerate. Okay, so now we can just fill in the forms. Let's go to the forms, convert. Okay, so we've got PS to DQ as the first form. This is going to match on XWord because it's a legacy encoding. The op-n for all of them is going to be RM, so op1 is going to be VEC, and op2 can always be VEC or memory. Then we have a prefix of some kind, so we've got prefix F3 for this case. F3. Then we've got the secondary opcode map. And then the opcode itself is, in this case, E6. So we'll just copy this for the VEX one. So family is going to be VEX in this case. We've got the same prefix and everything. There's no W set for any of these. And this is, oh, this is actually the wrong one. So PS to DQ is the one that I should be doing. PS to DQ. We've got 66 as the prefix and 5B. Okay, so this is actually prefix is 66. And then the opcode is 5B. 5B. And in this case, Z-word actually supports embedded rounding, so I'll have to separate that one out. So we've got EVEX, which, and VEX can also support Y-word. EVEX can support X-word and Y-word. These can have op masks and zeroing on the first operand, so we've got op mask and zeroing. All of the EVEX ones can support broadcast, but there's another one which is Z-word, which not only supports broadcast, but it also supports, in this case, ER for embedded rounding here. So let's just make sure that those ones move on to the next thing. Okay, so here we've got some incorrect encodings. So we've got EVEX and X-word, Y-word. So this is for VCVT. Okay, I think that is because in my tests I've forgotten to put on the op masks. So for all of these ones, V0 needs K, K1 and Z. Okay, so now it's moving on to the truncated version. And so the truncated version here, PS to DQ, is just F3 with 5B, and no W is set, but SAE is what we're supposed to be supporting instead. So the truncated version, let's just take this. We'll take both of these because it's going to be basically the same. So the opcode is still 5B, but the prefix is F3. And instead of SAE, we're going to support, or instead of ER, we're going to support SAE. And I just need to update these names because I copied them. Okay, so now we're getting an incorrect thing here for SAE. So it looks like we've got the prefix P0, P1, P2. So P2 we want 99, but we're getting D9. So let's just go to the EVEX layout. So P2 here, we're getting D9. So if this is C, then D would be that I'm setting this one like this, and then 9 is going to be this with these. So this one is correct because I'm setting K1, which is this AAA here. And then this one is also correct because this is inverted. So inverted means that it's not extending the V register, which is not being used. And when it's not being used, you need it to be set to 1. So what I've got here is D, but what I actually want is 9. So in the case of 9, that means I shouldn't be setting this L bit here. Which I guess makes sense because if I'm setting EVEX.B for SAE, this is only available on the ZMM1 anyway, so it looks like NASM is basically just saying ignore these L bits. I don't know if these are set if it will cause an undefined exception or something, or if this is just like a canonicalization situation. But either way, to match NASM, I'll just ignore those bits if SAE is set. So we'll go to the encoder, look for SAE. So basically we'll say that if not RM is SAE, then we'll only set the LL if it's not SAE, otherwise it will just be left as 0. Okay, so now we're on to the next form, which is DQ to PS. So DQ to PS does not have a truncated version. So I think if I just copy these ones from up here, this one is now DQ to PS. So we've got DQ to PS. And then we'll just go and look at the forms. So convert DQ to PS is there's no prefix at all for any of these. W is not set at all because we're not using PD, and then it's just 5B. So this is just the same thing but without the prefix by the looks of it. So we'll just get rid of this prefix here. And then we're supporting ER, which is fine over here. So let's just check that. Okay, so now we're moving on to PD to DQ. So these ones are all going to be basically the same sort of thing. These ones, but instead of PS, we're doing PD. So this should match on all of them, but be incorrect encodings. So I think for these ones, if we go and look at the PD ones, so we've got DQ to PD. So in this case, W is not set for these ones. Where is PD? PD to DQ. PD to DQ does have W set, so let's just do that first, but that's only for EVEX. So this is PD to DQ. So for these two here, we need W to be set to 1. Then the other PD one is, so we've got PD to DQ, DQ to PD, and then we've got PD, oh, there's a truncated version as well. Okay, so truncated version, PD to DQ also has the W bit sets. So actually I need to set them down here as well. So W needs to be W1 in these cases. This case it's 6.6 with E6 is the truncated version, which is this one. So this is 6.6 with opcode E6. It's probably going to be E6 for the other ones as well. PD to DQ, PD to DQ. Let's just do E6 on these because it's probably the same. So this one is prefix 6.6, this one is opcode E6, and W is set to 1. Then we've got PD to DQ without it being truncated. This time the non-truncated version is actually prefix F2. So we've got F2 here with E6, and then W is set as well for the EVEX versions, so we've got W as W1, and then DQ to PD DQ to PD is actually not W1, so this one is incorrect actually. So let's just go and get rid of these. This is still E6, but it has a prefix of F3. So now we've got some incorrect stuff here. So, okay, this is just missing the prefix again on this one. Okay, so now it's just PS to PD, which we'll do as PS to PD. So here we have no prefix, but we've got the same opcode map. So no prefix, opcode map 2, but this is 5A. And then we need to do, I'll just take the, let's see, we've got 5B up here, for example. So this is converts. I'll just take these ones. So these ones are also no prefix. And we have SAE support for this one. And instead of 5B, we've got 5A. So now it's just PD to PS, which I'll just take a copy of these ones and just change the mnemonic around. So this is PD to PS. So for PD to PS, we have a prefix of 66 for these ones. So let's just find map. Prefix is prefix 66. And then we've still got 5A here, and this time instead of SAE, it's embedded rounding. And then I think this DQ to PD one did not support any embedded rounding at all, so we'll take that off of there. Now we've just got some incorrect things for PD. Let's see, we've got F3 is, let's see, this is a PD to PS. PD to PS is 660F5A. So they've all got 5A here, 0F, they've all got 66 here as well. So that all looks correct. 660F5A, 660F5A, that's all fine on those. K masks. Let's see, we've got P1, in this case P2 looks like it's, this is because probably W bit is set to 1 on EVEX. Okay, so because the P1 is, in this case, you know, it wants P1 here to have F, whereas I'm giving it 7. So because it's got 7 is the low 3 bits, F means that the high bit one will be set here, so this is the W bit here, which needs to be set to 1. But only for EVEX, so we'll do W as W1. Okay, and that's all of the packed conversion instructions.